this time I'm gonna do it for the homework problem. And I haven't looked at this for a while, which is deliberate. I've done it before. So I'm not coming at this cold. But I frankly kind of I want you to see the process that I go through when I revisit this problem. So this is page 172, problem 65. And in this problem, we have Josh. He starts his sled at the top of a 3-meter high hill that has a constant slope of 25 degrees. All right, I can draw that already. Here's my hill. I have a slope of 25 degrees, and there's Josh plus his sled. Okay, and he goes down the hill, and then he hits a horizontal patch of snow, and slides on that for a while. And it says ignore friction on the hill. So I honestly didn't do that.
Yeah, Windows did it.
I know. I don't think Windows did it. I think
No, Windows decided what you like.
no. I think unfortunately I think it was my pen that did it. Okay. So we know there's no friction on the hill, so that's handy to know. But we were told the coefficient of kinetic friction between his sled and the horizontal patch of snow. So the coefficient of kinetic friction here is about 0.05. And some of you who are like unit people are thinking, wait, what's the units of that? Is that newtons? Is that what the coefficient of friction is a ratio. It's unitless. Okay, now what we know is, holy cow, we don't know anything about Josh's mass. We don't know. Holy geez, this is going to be pretty tricky. How do we figure this out without any masses? Well, we're just going to use variables. Okay, so here is my initial setup. Now, here's where things are going to get kind of interesting. There are a couple ways to approach this problem, one of which is going to be far easier than the other. One way to approach this problem is I can say, well, I need to set up a set of reference axes. And I know I have, like, the force of gravity is always going to be straight down. And at the bottom of the hill, Josh and his sled are going to be moving straight to the right. There's going to be a normal force that's straight up, and the force of friction is going to be straight to the left. So it actually makes a lot of sense for me to use the same reference axes that I did before. And I could do that. But as it turns out, if I think about this as kind of having two parts, it actually makes sense to look at the first part of our motion here, first part of our action, as being on a different set of reference axes. And there's no reason that I can't do that. The reason that it's kind of handy to use a different set of reference axes over here is because if I look at my normal force, it's perpendicular to the hill. If I look at the motion of Josh and his sled, it's parallel to the hill. If there were friction, which there's not in this case, but if there were, it would also be parallel to the hill, which means that we would have a couple forces and the motion would be parallel and or perpendicular to the hill. So it makes a lot of sense for us to use, for the first part of this problem, a set of reference axes that are aligned to the hill. So that's what we're going to do, which means, despite the fact that we only have one set of objects here with one mass, we're going to use two different free body diagrams. This is effectively two separate problems. And we haven't done this yet. This is a new thing. So those of you who tackled the homework, might not have realized that that was something you could do. And that's fine, you can still solve the problem, but it's gonna be easier if we think about it this way. So let's make our free body diagrams now. So we're gonna have two. We have one free body diagram for the whole system, and we'll just say that that has a mass of m on the hill. When it's on the hill, there is a normal force perpendicular to the hill, and there is the gravitational force pulling straight down toward the ground. And that's it, there's no friction here. And it is true that the sled is moving, but there's no force of motion. Motion itself is not a force, motion is motion. Pushes and pulls are things that could potentially change motion. There's only two forces acting on this object, the way it's described in the problem. Once we're off the hill, then we have three forces. We have the weight, we have the normal force, and we have the force of friction, okay? So there's our setup, and our next step is always to look at our forces and make sure that they're aligned with our reference axis, and if they're not, then we break them into components. And that's where we've got another new piece here, because this force right here, this downward force, is not aligned with either my y or my x-axis. So I have to break it into components, and you know how to do this, we've done it before. That's this trick, where there's always gonna be these two components. This angle is always gonna be equal to the angle of the hill. The component that's parallel to the hill is gonna be mg times the sine of the angle. The component that's perpendicular is always gonna be mg times the cosine of the angle. Some of you have the geometry and trig background to understand this, which is great. Those of you who don't have that background, just know this, write it down. You can use it, you can take it to the bank. It's always gonna be true for an object on a slope. You know the angle of the slope with respect to the horizontal, that's gonna be the same as this angle right here. This diagram is your ticket, okay? And over here, our free body diagram, all of our forces are aligned with our reference axes, okay? So, all right, let's see what we can do next. So the next step is to use Newton's second law, and we have four different cases to consider. The first is the x-axis forces while Josh and the sled are on the hill. The second case is the y-axis forces while Josh and the sled are on the hill. The third case is the horizontal forces when they're on the ground, our x-axis forces on the ground. And the fourth case is our y-axis forces, the perpendicular forces when Josh is on the ground. So in all of these cases, the sum of the forces is going to equal mass times acceleration. In this case, we have only one force component acting in our horizontal dimension, and it's in the positive direction. So that means Josh's mass times g times the sine of that angle will equal Josh's mass times the acceleration in the x dimension. Okay. And our second set of forces are the perpendicular forces when Josh is on the hill. The sum of those forces will equal Josh's mass times his perpendicular acceleration. And this is a case where, because we chose a reference axis where one of our axes is perpendicular to the hill, it's a little bit misleading, because when you look at this, you're like, oh, well, he's going down, so maybe there's some downward part to his acceleration. That's true. There is a downward part to his acceleration. But we don't have a perfectly downward axis. We have instead a perpendicular axis. And if you look at where Josh is on the y-axis, he's always going to be in the same location. If we had Josh start at y equals 0, then Josh is gonna end up at y equals 0. And this is where it gets to be a little bit of a brain buster, because our brains are conditioned to think of y as being up and down. But y isn't up and down. Y is perpendicular to the hill. If you think about Josh moving along this axis, he's not going up or down relative to this starting position. So in this case, the acceleration is 0. And we have two forces. The normal force is in our positive direction, and the perpendicular component of his weight is in the negative direction. So in this case, the normal force perpendicular to the hill is going to be equal and opposite to this perpendicular component of the weight. And then we have two more equations that we can set up. One has to do with Josh's acceleration once he's on the flat and the forces acting on him. So in that case, it's the force of friction in our negative direction, and Josh's mass times his acceleration, which, if you look at what's going on here, you can tell instantly that if we're using the conventions properly, this is going to be a negative number. His acceleration has to be a negative number. It has to be. And then in the y dimension, the sum of the forces will equal Josh's vertical acceleration. Well, he's just sliding along the ground. He doesn't go up, he doesn't go down, there's no change in his motion in that dimension, so this is going to be 0 as well. So that means our normal force in the positive direction plus Josh's weight, the force of gravity pulling Josh and the sled down in the negative direction, are going to sum to 0. Okay? So there's our equations, and let's just look at these separately for a moment here. We're going to work through these equations. Ultimately, we're going to need to think about these free body diagrams as well. So this is not two separate objects, right? Like this is on the hill and this is on the flat, okay? But they are like four unique equations, four relationships. Some of these numbers are going to be the same though. Like m is always going to be the mass of Josh and the sled together. G is always going to be the free fall acceleration of an object in the Earth's gravitational field. So some of these numbers are going to be the same, but these relationships are going to be different. The normal force while Josh is on the hill is going to be different from the normal force when Josh is on the flat. The normal force increases. There's a greater supporting force when he's on level ground. On the hill, it's smaller. On the flat, it's bigger. Okay, so let's see where we can get with this. So what we're going to do is just try to simplify some things and think about the stuff that we know and the stuff that we don't know. One thing that we can do here with this equation is recognize that, well, we can divide both sides by Josh's mass. Now, you can't divide by 0, but you can divide by a positive number. We know his mass isn't 0, so we know we can divide by that variable. We know theta, it's 25 degrees. We know g, it's 9.8. We can find Josh's acceleration. It's going to be g times the sine of the angle. While he's on the hill, he's going to be accelerating at a rate that doesn't depend on his mass at all. Any object in a frictionless environment going down a hill will accelerate at the same rate. If we look at what's going on in the vertical dimension here, we're gonna, or in our perpendicular dimension, we're gonna determine that the normal force is equal to mg times the cosine of theta. We don't know m. We don't know the normal force. that's really not that helpful. There's no friction in this setup. There's not really anything we can use here that's gonna be of value to us, all right? Okay, so we've got one relationship here that's gonna be useful. We've got one relationship that isn't gonna be helpful at all. We don't have enough to figure it out. And then here, what the question is asking ultimately is how far from the base of the hill does he end up? So we need to know something about the acceleration, but the problem is we still don't know his mass. So that's gonna be an issue, but we'll come back to that in just a second. And here, it's the same deal, like we've got the normal force, we've got the mass, and we've got some problems that we need to work out. And remember I said, friction is just a force. So when we built our free body diagram, we just put friction in as a force. And I just said friction was like in the negative direction because of our frame of reference. And it was just another force we could look at. And here's where we're gonna add a piece to the puzzle. And that is that friction is actually related to the normal force. We have one more equation we can use down here on the flat that's gonna be helpful. And that equation is that the force of friction is gonna be equal to the coefficient of friction times the normal force. And if that's true, then we can do some fancy substituting here, okay? Because we know for this green equation, the force of friction is going to be equal to mass times Josh's acceleration in that x dimension on the horizontal. The force of friction is going to be negative mu k times the normal force. And with our blue equation down here, we can just calculate that the normal force has to be equal and opposite to the weight of Josh and the sled. So that means negative mu k mg equals max. And once again, we can divide both sides by m. And we're gonna find that the acceleration on the flat is gonna be negative mu k times g. So we now have two equations that we can use. Now keep in mind, this acceleration is on the slope. It's speeding Josh up in the positive direction as we defined it on the slope. This ax is on the flat, and we know it's going to be negative because it's got a negative sign in front of two values that are going to be positive, and we knew it was going to be negative to begin with. He's slowing down. But we could find both of those accelerations, right? So that means that we can find Josh's acceleration down the hill is going to be equal to g sine theta, which we know, and we can find acceleration on the flat. It's going to be equal to negative mu k times g. We have all this information. We can get a number for acceleration here. We can get a number for acceleration here. And the forces part of this problem is solved now. Now we have two accelerations. And what else are we trying to find? Well, what we really want to know is how far is he going to slide at the base of the hill? And I'm not going to do that right now just because it's getting late and I've been talking for a while. But what I want you to recognize is this is two kinematics problems now. And they're ones that you've done before. This one, we know a distance. The hill is 3 meters long. So with a starting velocity of 0, a hill that's 3 meters long, with this acceleration, we can find how fast he's moving at the bottom of the hill. And then with this acceleration and a starting velocity We know what we're looking for is an ending velocity of 0. We can find how far he's gonna move with the starting velocity that we computed here at this acceleration. So, and I'm not gonna do that now, I will do that for you probably tomorrow actually, just so you can see it, but at this point, this is the forces part of the problem. So what I want you all to recognize here is that this system works every time, but what you all need to be doing is practicing. And the practice is where things are gonna start to gel for you. So the practice has been happening, we've been doing a bunch of work, we've been making free body diagrams, but we're escalating the complexity. So we had a perfectly horizontal and vertical problem before. Here is an example of a problem when there's sort of a mix of like 2 different frames of references to use. And then what I'm gonna ask you all to do for the final activity is think about an even more complex setup. So